Good morning, my dear students. In today's class, I am going to explain one of the application of the FMCW radar. The FMCW radar can be used as a radio altimeter. The application is FMCW altimeter. It is used in the aircrafts to measure the height between the surface of the earth and aircraft. Because of the large backscatter cross section and relatively short ranges, these type of altimeters requires low transmitter power and low antenna gain, and the relative motion between the aircraft and the ground is small, and the Doppler frequency shift can be neglected, and the frequency range that is reserved for the altimeters is 4.2 GHz to 4.4 GHz. And we will see the block diagram of FMCW altimeter. The FM transmitter generates a frequency modulated signal where the frequency of the carrier is going to be changed. And then for the mixer, we are going to give two inputs. One is FM signal, another one is local oscillator signal. The mixer generates original frequencies and sum of frequencies and the difference of frequencies. F0 of t is original frequency, F0 of t plus FIF, F0 of t minus FIF. And then this sideband filter will select only one frequency, that is difference frequency. You can select any frequency, but in this block diagram, we are selected the difference frequency, F0 of t minus FIF. And for the receiver mixer, we have two inputs. One is echo signal. The echo signal is F0 of t minus t, and another one is local oscillator signal. The local oscillator signal is F0 of t minus FIF, and the receiver mixer will generate the difference between these two frequencies. The difference between these two frequencies is F0 of t minus FIF minus FIF. It will give FIF plus FB, where FB is beat frequency, that is equal to F0 of t minus F0 of t. The echo signal frequency minus transmitted signal frequency, nothing but a beat frequency. The mixer output is intermediate frequency plus beat frequency, and this IF amplifier allows the intermediate frequencies and the frequencies around the intermediate frequency, and balanced detector will eliminate the high frequency component and allows only low frequencies. The low frequency signal is a beat frequency signal, and this beat frequency consisting of both range frequency and Doppler frequency, and range frequency is measured with the help of a average frequency counter. It will give the range or height between the surface of the earth and the aircraft. The height between the aircraft and surface of the earth is measured with the help of a average frequency counter, and Doppler frequency is measured with the help of a switched frequency counter. It will give the Doppler velocity. Average frequency counter gives the range, and switched frequency counter gives the Doppler velocity. This is about FMCW altimeter. And the next concept is multiple frequency CW radar. Normal CW radar cannot measure the range, but it is possible to measure the range by measuring the phase difference. Suppose we are transmitting the sine wave sine 2 pi f0 t, and received echo signal is sine 2 pi f0 t minus t. This is the transmitted signal, and second one is echo signal. It is in the CW radar, and the phase difference between these two is 2 pi f0 into t. Already we know that the time is 2r by c. By substituting that, we can get 4 pi f naught r by c. And from this, if the phase difference is known, you can measure the range. Therefore, range r equal to c into delta phi by 4 pi f naught. That is equal to wavelength lambda by 4 pi into delta phi, because velocity of light by frequency gives lambda by 4 pi into delta phi. For the unambiguous range measurements, to measure the range correctly, the maximum phase difference is 2 pi. That means the delta phi is 2 pi. When delta phi equal to 2 pi, the range is lambda by 2. That means very, very small. By using CW radar, you can measure very, very small range. That means 3 millimeters range, 1 millimeter range, that have no interest, that have no use also. The range of this CW radar can be increased by using transmitting two separate frequencies. One is one frequency with f1, another signal with frequency of f2. First signal is transmitted with a frequency of f1, and second signal is transmitted with a frequency of f2. And the echo signal will have a Doppler frequency shift. First echo signal is v1 of r, that is equal to sine of 2 pi f1 plus or minus fd1 t. This component is the phase shift 4 pi f1 r naught by c plus phi 1. And the second echo signal is v2r, that is equal to sine of 2 pi f2 plus or minus fd2 t 4 pi f2 r naught by c plus phi 2. This is first echo signal and this second echo signal. And where r naught is the range to the target at a particular time t equal to t naught. fd1 is the Doppler frequency shift associated with the frequency f1, and fd2 is Doppler frequency shift associated with frequency f2. And the receiver separates the two echo signals, and after the second detector, the first component is v1t, that is equal to sine of plus or minus 2 pi fdt minus 4 pi f1 r naught by c. And the second signal is sine of plus or minus 2 pi fdt minus 4 pi f2 r naught by c. These are the signals at the output of the detector, and these are the two signals. And 4 pi f1 r naught by c is the first signal phase shift, and 4 pi f2 r naught by c is the second signal phase shift. Therefore, the phase difference between two signals is delta phi equal to 4 pi into f2 minus f1 into r naught by c. f2 minus f1 is nothing but a frequency deviation delta f, that is equal to 4 pi delta f r naught by c. By using this equation, we can measure the range r, because phase difference we can calculate. We know the phase difference, and we know the velocity of light, we know the frequency deviation delta f. That means we can measure the range r naught. The range is given by c into delta phi by 4 pi into delta f. Already we know that for unambiguous range measurements, where delta phi equal to 2 pi. For unambiguous range measurements, delta phi equal to 2 pi. By substituting delta phi equal to 2 pi, we can get the unambiguous range. The unambiguous range is c by 2 delta f. For CW radar, The unambiguous range is very small, lambda by 2. It is a very small, that is in the millimeters. That small range having no practical interest. But by using by transmitting two separate frequencies, we can increase the range of the CW radar. The maximum unambiguous range is C by 2 into delta F. That is the advantage of multiple frequency CW radar. We can measure the range of a target. Okay, this is about today's class. Thank you very much.